All right, we are on to our last topic that we have here in 254, which is triple integrals. We have two sections on triple integrals. We're going to start with looking at triple integrals in rectangular coordinates. And again, that's our normal sort of XYZ coordinates that we're used to. Um, so we'll look at what those triple integrals mean, how those get set up, and then we'll also use them to find volumes like we were in the last section, but with triple integrals instead of double integrals. And this is similar to what we did when we were finding um, area between two curves with the double integrals. All right, so with our triple integrals, let's go back first and think about, again, what that double integral told us. This gave us the volume under a surface, or if we did the double integral of 1 over our area, that gave us the area of the region that we were interested in looking at. So we can, again, kind of take this idea that if we've got a function inside of our triple integral, that's going to give us a volume under our four-dimensional surface. And if we've got a triple integral, but instead of a function, well, or we just have the constant function 1, that's going to be another way that we can find the volume under a surface. And sometimes it's going to be nice to do that volume that way because it's going to help us get things set up in the right way. And it's just going to help us out a little bit. So, sort of the general way that they look is we've got the triple integral. So that really is three integrals that we're going to have to take. We've got our function f, and it's going to be in terms of x, y, and z. So it's a four-dimensional function. It's going to output a fourth variable, w, or whatever we want to call it. And then we've got dv. So we're integrating over a volume. We'll talk about what dv is here in a second. Our limits of integration, how they are going to look is that our innermost limit of integration is going to be at most in terms of two variables. It's, likely going to be x and y, but it could be y and z, or it could be x and z. It could be any of those. The middle integral is going to be at most in terms of two variables, or one variable, excuse me. We already did two variables. This is going to be at most in terms of one variable. And it's likely to be whatever our last variable that we're integrating over is. So the first, this most inside integral, if we're integrating with respect to z first, these functions are going to be in terms of x and y. If we're integrating with respect to y first, then we're going to be in terms of x and z here. If we're integrating with respect to x first, then we're going to be in terms of y and z here. So these functions here are not going to include the variable that we're actually integrating with respect to. Same here. This is our second integral, and this is going to be one variable. And if we're integrating with respect to x, these variables better not be x. And when we get out here to our last one, these are going to have to be constants. If they're not, then we're not going to get a number out as an answer, and that's what we want. We want a number. These are definite integrals. They need to give us an answer. So the question is, what is dv? Well, when we're looking at our region in terms of x, y, and z, it's going to be a three-dimensional region. So our region is going to look something like this. It's going to be some sort of shape that we've made. In this case, this is sort of a triangular solid here, but we want to do what we've done always with our integrals. We want to take whatever our region is, whether it's a 2D region, 3D region, or essentially kind of the 1D region when we're looking at this, when we're just integrating, doing a single integral. We always take that region and we slice it up, whether it's slicing it into those big long rectangles or our little rectangles. Um, Sorry about the ding. My daughter texted me in the middle of this and my sound is on my computer. Um, so when we've got this 3D region that we're talking about, because that Now our region is going to be a volume, which is going to be kind of weird to think about, but we're going to divide that up into smaller cubes, or we could say, we could be a little less specific and call them rectangular solids, but we're going to look at what the volume is of each of those little individual, you can think about it, it's a bunch of cubes, and we're going to use those cubes to approximate the region that we have. So dV is going to be, you can kind of see it down here in the corner here, our change in volume, how each of those cubes change, it's going to be the change in the length times the change in the width times the change in the height. So this is going to be dx, dy, dz. Now we can write these in different orders, and there are several different orders. Let's see how many of these can I do. There's a couple, that's not all of them. I don't even know if I want to get all of them, but that's not all of them, I don't think. There might be another one that I'm missing there. Um, and oh, maybe it's this one, dx, dz, dy. So double check, see if I'm missing one of them. I might be. Um, but we can integrate in whatever order is most useful for us. Now, most of the time it's going to be dy or dz, dy, dx. Most of the time, this first guy here, that's going to end up being our order. But we can do this in whatever order we need to, just like with that double integral, we can flip and flop them. All right, so ooh, this one already, we've got one that's set up a little different. We're going to integrate with respect to z first, then x, and then y. So again, what that means in terms of that region that we're integrating over, this is telling us that, let's grab some different colors here. So that most inside differential goes with our most inside integral, and then our middle differential goes with our middle integral. And then our outside differential goes with our outside integral. So these limits of integration tells us that y we're going to look at from 1 to 2, and x we're going to look at from 2 to 3, and z, that one was green, yep, z we're going to look at from 0 to 1. So that's going to make over here a rectangle that we're integrating over. So our surface is actually going to be a rectangle, and sometimes it is and sometimes it isn't, because of course we can, define these with functions instead of straight lines. So I kind of draw these straight lines out here to kind of get the idea, at least in the xy plane, of what we're doing. So there's our region there, and then it's going to go up 1 in the z direction. So there's our little rectangle. That's our volume that we're integrating over. That's our region. And so what we're going to do with this is what we have been doing. I'm going to take this innermost integral and compute that first. And again, you can do these all kind of at once as, big triple integrals, but I like to take these a piece at a time. And when we're doing this integral, we're going to treat x and y just like we would treat that 8. This whole piece right here, this whole unit, that's our constant term. And we're just going to integrate the z. So we're going to get 8xy over 2 times z squared from 0 to 1. And we're going to use the fundamental theorem of calculus. We're going to get 4xy, and then plugging in z, and then minus 0. So we just get 4xy. And this is what should happen when we do these, that when we do that first integral with respect to z, all the things that have z should be gone. So now we're sitting here like this, that we've got now we've just got a double integral. So once we do that first integral, it's like what we've been doing before. So we'll take this one aside and integrate with respect to x. And so again, in this case, the 4 and the y, those we're going to treat like constants, and we're just going to integrate our x variables. So we get 4y over 2, x squared from 2 to 3. And then, of course, we need to plug in 3 and then minus plugging in 2. And we do get like terms here, so we can go ahead and combine those. And we're going to get 10y. I should double check that I'm right. So that 10y, we're going to plug that back in here into our double integral, and we're going to have the integral from 1 to 2 of 10y. And again, what should happen each time is that when you integrate with respect to z, your z should go away. When you integrate with respect to x, your x's should go away. When you integrate with respect to y, you should just be left with a number. All right, so we're down to the end here, and we can do this integral. So we get 5 times 2 squared minus 5 times 1 squared, and then this is going to be equal to 15. All right, so when we've got ones like this that are set up, not too bad. It's just one extra integral that we have to take. So now where this gets interesting is actually when we start looking at these to help us find volumes of these 3D regions. And so we're going to have to do a little sketching to kind of figure out what it is that's going on and figuring out what our limits of integration are. And we'll spend a little bit more time looking at how to get those limits of integration versus how we are going to actually, find the integral, because the hard part here is getting that integral set up. Once we've got it set up, we can integrate, and there's things that we can do to help us integrate. We all know about some nice fancy things that are on the internet that can help us integrate. So we'll at least get these set up, and I'll tell you what the answer is. And possibly let you go through that actual practice of doing the integral. So we want to set this up. So let's take a look at what this is talking about here. So first off, saying that we're looking at the volume of the region and we're bounding it by x equals 0, y equals 0, and z equals 0. So that's bounding it by our axes here, so that we're only going to be looking at, and actually I don't want to do that much, we're only going to be looking at this first octant. So we're basically looking at only when z, x, and y are all greater than or equal to 0. And then we've got our surface here. So this is a plane. We've seen graphs like this or equations like this before. There's no exponents on our variables, which means it's, sort of quote, we'll say in quotes, linear. So this is a plane, and what's going to help me graph this is actually figuring out what each of our intercepts are. So our x-intercept, that occurs when y and z are 0. So that occurs when x is 2. So there is our x-intercept. We can do the same thing for the y-intercept. That happens when x and z are 0. So that occurs when y is 2 as well. So there that is. And then z-intercept, again, occurs when x and y are 0. Sorry if there's any background noise there. My cat is being very annoying today. And I record in my bedroom, and she's in here, and they're awfully sassy in the morning. Okay, so the part of our plane that we're going to use is just this part that's in that first octant. So we can connect our intercepts, and it's just going to be this little triangle, and basically it's going to be this rectangular or triangular solid that we're going to look at. So what we need to figure out is our limits of integration. So I usually do start this out where I integrate with respect to z first, just because that's kind of what we've been doing and sort of how we've been setting this up. So what we want to think about is that we're starting here in the xy plane with z being 0 and then going up until we hit our surface here. And that surface, we could get that surface in terms of any one of these variables if we wanted to. It's actually going to be easiest to get that surface in terms of z, because all we have to do is subtract 2x and 2y from both sides, and we've got it solved in terms of z. So our limits of integration for z, we're going to go from z being 0 until we hit our plane, like that. So now the next thing that we need to think about, oops, no, I think we're okay. Most of it's still on there. It's hard to erase when there's other things going on there. And so now we can integrate with respect to x or y. It really doesn't matter. Again, my brain, I like to integrate with respect to y first, because again, that's kind of what I'm used to. And what I do sometimes like to do is think about what's happening in the xy plane. And in this case, if that's x and that's y, what's happening in the xy plane is that we're looking at this region right here. Right? That's our region down here in the xy plane. And when we're looking at integrating with respect to y, we are going from 0 until we hit that line right there. That line is y equals negative x plus 2. So our limits of integration for y is that we're going to go from 0 until we hit that line, negative x plus 2. Or you can write it as x minus, or 2 minus x. That's fine too. And then our limits of integration for x, this is where we're now finally on an axis, and that's going to go from 0 to 2. So our triple integral is going to be the integral from 0 to 2, the integral from 0 to negative x plus 2, and the integral from 0 to 4 minus 2x minus 2y. And again, this is not the only way to set this up. You could have started integrating with respect to x and started over here and saying, okay, I'm going to start in the, oh, well, this would have been with respect to y. Starting over here in the xz plane, if I'm integrating with respect to y, starting with y being 0, and again, until I hit that plane. And then we could look at what was happening in the xz plane. So you can set this order of integration however you want, but that does change. It's going to alter your limits of integration a little bit when you do that. So our function that we're integrating over, remember when we were finding the area of our surface, we would integrate the function 1. That's exactly what we're going to do here. If you integrate with your function being 1, that's going to give you this volume of that region that you have. And we've got dz, dy, dx. So again, remember this order here that we put dz, dy, dx, that has to match the order that we put our limits of integration. So when we do our first integral, I'll at least do this one because this one's pretty easy. 1 dz, we are going to get z from 0 to 4 minus 2x minus 2y, and so that's going to be 4 minus 2x minus 2y. So this really is like our triple integrals that we're, or double integrals that we're used to doing in the previous two sections, because this really just sets up that volume. And this does give us a way that if it's easier to set this up, not starting with z first, but maybe starting with y or x, because it might be, depending on the functions that we're given to look at. So it might be easier to set it up that way. So this just gives us some options with our limits of integration. And now we can go about this double integral. Again, I will save us, and so we'll go work here. And this is going to be equal to 8/3. And our units here are cubic units. Our units on our previous slide back here, this would be units to the fourth. It kind of doesn't totally, it's another one of those times where we're like, what is going on here? Because it doesn't kind of work with our brain of what's happening here. And this guy is called a hypervolume because, you know, we have to think about things in 4D, which we really can't do. But we do often get these kinds of functions to talk about, say, like temperature in a room. You know, if we're talking about sort of an output in a three-dimensional space. So you can think about if we take a room, which is a three-dimensional space, and then find the temperature at different places in that room, we'll get different temperatures based on where we are in the room. So if you think about moving around that three-dimensional space and getting temperatures, that's the kind of function that we've got here. This is also, you can do this with density of an object. Um, you know, if you have an object, it can have different density at different places in that object. So you can think about, okay, if I'm at the spot 1, 2, 4 in my object, it's going to possibly have a different density than if I'm at 2, 7, 5. So if we orient those objects in the XY plane. All right, so let's find another volume again, at least getting this set up and drawing that picture and sort of thinking about what it is that we've got and, you know, what makes sense, to, you know, in terms of our limits of integration. So we've got to find the volume of the region y equals x squared, z equals 0, z equals 4, and or y equals 9. So these are giving us, again, sort of our boundaries for our region here. So z is going to go from 0 to 4. 1, 2, 3, 4. So we're going to, again, that's kind of taking off any of this part down here. And so it's going to start in the xy plane and go up until z is 4. And then we've got this function here, y equals x squared. That's a function that is in the xy plane. Oh, if I go too slow, it makes a straight line, and I don't want to do that. So here's y equals x squared. That's a parabola. We know what that looks like. Kind of have to think about our regular xy plane, again, lying on the floor there. And then we've got our other limit here that y is equal to 9. So if we put 9 here, this is a horizontal line. And this is our other boundary, so maybe we need to make this go here. So where this is going to hit right here, that's going to hit at x being 3 and x being negative 3, right? When you've got an output of 9, your input was either 3 or negative 3. And so that's our bottom boundary. So our top boundary is actually going to be that same shape, that same parabola shape. Ooh, this is how well can I draw in 3D today. Going down there, hitting at 9, going across there. This is not too bad. There we are. We've kind of got like a parabola that we've made tall and, given a thickness to it. Okay, so this is our region. And, looking at, some of the limits of integration that we have, right here, z is going from 0 to 4. So that's telling me that that might actually be our last limit of integration that we're going to set up. X is going from negative 3 to 3. Y is really the one that's got an equation on it. So I'm actually going to make that my first limit of integration. And if you look at what's happening with y, when we're going on the y-axis here, it's going from our parabola to that line y equals 9. So it's going from x squared until we get to 9. So those are going to be our limits of integration. That lower bound is that parabola, and our upper bound is that line y equals 9. And we can see again, similarly going and moving along the x-axis, our lower bound is 3 and our upper bound, or negative 3, and our upper bound is positive 3. Similar on the z-axis, our lower bound is 0, our upper bound is 4. And so when we're setting up our integral here, it really doesn't matter if we do x first or z first, in terms of sort of the second part of this. The only thing that needs to be first, or should be first, not fist, how about first? Should be first, is y. And in particular, we need it to occur before x, before we have dx. And that's because one of our limits of integration has an x in there. So if we integrate with respect to x first and then integrate with respect to y, those limits of integration on y, that's going to introduce an x, at least how we have them set up right now. There could be ways that we could set this up so it doesn't do that. But at least how we have them set up right now, if we did x first and then y, doing that fundamental theorem of calculus with respect to y, we're going to introduce an x. So then we wouldn't get a number for our volume. So when you've got one of these limits of integration and only one of them has variables, do that one first. Get that one out of the way. And again, we're going to integrate the surface 1 because that's going to give us this volume. And our order is going to be dy, dx, dz. And you can absolutely flip around this order, particularly with x and z with how we have it. It does not matter one bit the order that we do that in because both of those are constant. So we can do those in either order. That really, really doesn't matter. And I didn't write the 1 here, but remember it's there when we don't write it. Even when we don't write it, it's there. And again, no matter what happens, with these other two, when we do this first inside integral, the integral of 1 dy from x squared to 9, we're going to get y from x squared to 9, and that's going to give us 9 minus x squared. So then our integral, I'll at least do the one I underlined here, 9 minus x squared dz dx. So we can do that again, or we can do 0 to 4, negative 3 to 3, 9x squared dx dz. Either one is going to be fine. I probably would do, if I had a choice, I would probably do it this way first because that's going to get rid of that x. And if I integrate with respect to z right now, um, what I need to do is, excuse me, my my brain stopped there for a second. I would have to treat this 9 minus x squared as a constant, and that would be, kind of annoying. So I don't want to do that. If I do with respect to x next, then all of that goes away, and it makes, it's going to make things nicer when I integrate with respect to z. So we can go off to the side here and do this integral. And again, I'm going to save us the work on this and say you're going to get 36. And then we get the integral of 0 to 4 of 36 dz. And that's going to be much easier to do. That's going to be very, very simple. And you're going to get 144. And this is going to be units cubed. Okay, one more for us to set up. And I already have a picture here because this is a much better picture than I can actually draw. So this is going to be set up the triple integral. So we're just going to set this up to find the volume of the solid bounded by two surfaces. And again, we're just going to set this up because that is really the hard part of this. Once we've got this set up, like I said, there are certain internet websites that we could go to that could help us evaluate these integrals. And trust me, when I did this, I did have it help me evaluate those integrals. So because they're kind of gross. But we can, at the very least, get this set up. So we've got two surfaces. So this top surface right here, that is the z equals 6 minus 2x squared minus y squared. That's going to be an upside down paraboloid. So that, that shape should kind of make sense. And the one underneath, that is the x squared plus 2, and that's going to be a paraboloid that opens up. Again, that should make sense in terms of what we know about graphs and 3Ds. And what's also nice on this graph, what's drawn is where those two surfaces intersect, what that trace looks like. And if you notice down here in the bottom, it makes an oval. That's 1 and that's negative 1. It's making an oval in the XY plane. So we'll see that here in a second. So when we're thinking about setting this up, and what I would do is my limits of integration, I would integrate with respect to z first because I can see exactly what I'm integrating. I've got the bottom part is this bottom surface, and I'm going to integrate up to that top surface. So z is going to be bounded by those two surfaces, and I really don't want to solve those for a different variable. So those are going to be my limits of integration on z. So that bottom function is going to be the lower limit of integration, and the top function is going to be the upper limit of integration. And then when I look at y or x, again, it doesn't matter, but I generally like to set these up to integrate with respect to y next. That's a little bit how my brain works. And what I did to figure out what's happening in terms of the xy plane is to figure out what's happening along this place where our two graphs intersect. So if we set our two functions equal to each other, 2x squared plus 2 equals 6 minus 2x squared minus y squared, right? If we set those two equal to each other, and let's see, we add that to both sides. I know you guys love watching me do a little algebra. We get 4x squared plus y squared is equal to 4. So this is that ellipse that we're seeing. And notice for like the x-intercepts here, if you let y equal 0, you get x squared is 4x squared is equal to 4, so you get x is equal to plus or minus 1. You get y squared is equal to 4, so you get y is equal to plus or minus 2. So that's where we're getting that elliptical shape there. And when we're looking at y, its lower bound is again this bottom part of this ellipse, and we're going up to the top half of our ellipse. So if we take this ellipse and we solve it for y, and it's a little bit easier to solve it for y than it is for x, just because x has a coefficient. Y is bounded on the bottom by the bottom of that ellipse, and our y values are bounded on the top by the top of that ellipse. So that's going to be our limits of integration for y. And then our limits of integration for x, finally, we're off of the ellipse and just onto our axis, and it's going to go from -1 to +1. So like I said, we could have flip-flopped how we did these. We could have traveled on that ellipse with respect to x, and we could have solved it for x, and that would have given our upper and lower bounds for x. And then our bounds on y would have been -2 to 2. So you can set it up that way, but again, I think you get a slightly cleaner equation solving for y. And again, it's just because of how the coefficients are. So our triple integral will integrate with respect to x last. Our integral with respect to y is going to be in the middle because that's the one that has a single variable. And we'll integrate with respect to y first because that's the one that has two variables. And again, our function that we're integrating over is 1 because we're finding a volume. And we'll have dz, dy, dx. And this is a pretty yucky integral, but you will get 4 pi units cubed. And this should tell you that it's a slightly nasty, gross integral. You have to do some integration by parts, and you end up with an inverse sign, and oh, it's so super fun. Or I think it's a sine function somehow in there, which is how you crazily get a pi in there, because it doesn't look like you should have one at all, but you do get one in there. So this one might be one that we revisit again, looking at with some of the other ways that we can set up our coordinate plane that might give us an easier integral. We'll take a look at that, but we're about to the last section. So we're going to look at what would cylindrical coordinates look like in 3D or spherical.